1 minute ago, a machine on top of a Chilean mountain did something no human eye has ever done. It looked at the night sky and saw 800,000 things change in a single night. Not stars twinkling, not clouds drifting. 800,000 individual cosmic events. Explosions, vanishings, objects that simply were not there before. Flagged, catalogued, and sent racing across the world in real time. And the strangest part? Most of humanity has no idea this is happening right now, every single night, above their heads. Somewhere in northern Chile, at over 8,000 feet above sea level, there's a structure that looks more like a sci-fi fortress than a telescope. It sits alone on a mountain called Cerro Pachon, wrapped in cold desert wind, staring upward with a camera the size of a small car. This is the Vera Rubin Observatory. And what most people are not seeing is that this is not just another telescope. This is something closer to a surveillance system for the entire universe. Think about what that means for a second. For all of human history, we have looked at the sky in fragments. A photograph here, a glimpse there, astronomers pointing instruments at one tiny patch of darkness, hoping something interesting happens to be there. The universe has always moved faster than we could watch it. Supernovae exploded and faded before anyone noticed. Asteroids drifted past Earth, unseen, undetected, gone. We were always a few steps behind the sky, but that gap, the one that has existed since the first person looked up and wondered, just collapsed. Here is where it gets unsettling. In just over 10 hours of test observations, not even real operations yet, just a trial run, this machine detected more than 2,000 previously unknown asteroids in our own solar system. Read that again. 2,000 objects drifting through the same neighborhood as Earth that no human being on this planet knew existed until a camera in Chile noticed them in less than half a day. For context, every other observatory on the planet combined, working all year, discovers around 20,000 asteroids annually. This single machine, in its first test run, found over 10% of that number before its real mission had even begun, and that was just the warm-up. By the time the system moved from testing into its actual nightly operations, the numbers stopped looking like science and started looking like something out of a control room in a thriller. On a single night in February of this year, the observatory's new alert system went live and immediately fired off 800,000 notifications. In one night. Each alert representing something in the sky that had changed. Brightened, dimmed, exploded, moved, or simply appeared where nothing had been before. According to the people who built the system, this number is expected to climb. Officials overseeing the project have stated they anticipate the observatory could eventually generate up to 7 million alerts every single night once its full 10-year survey is underway. 7 million, every night, for 10 years. Sit with that figure for a moment, because this is where the real story begins to take shape. What does it mean when a single instrument on Earth can generate 7 million individual data points about the sky in 24 hours? It means we are no longer studying the universe the way we used to. We are now monitoring it, continuously, automatically, at a scale no human team could ever process manually. This is not stargazing anymore. This is something closer to planetary scale reconnaissance, and it is being run by an alliance of American science institutions with a level of technical ambition that very few people outside the astronomy community have fully grasped. But here's where it gets worse, or depending on how you look at it, where it gets far more interesting. The camera at the heart of this operation is not just large. It is, according to the engineers who built it, the largest digital camera ever constructed by human beings. A 3.2 gigapixel sensor paired with an 8.4 meter mirror, capable of capturing a field of view roughly 40 times the size of the full moon in a single exposure. To put that into perspective, if you tried to display one full resolution image from this camera on a standard high-definition television, you would need around 1,500 separate screens just to show the whole thing at once. This is not an exaggeration for dramatic effect. This is the literal scale of the hardware now pointed at the night sky, 24 hours a day, on a rotating schedule designed to scan the entire visible southern sky every 3 to 4 nights without pause for the next decade. And this is where the story shifts from impressive to genuinely strange. What most people are not seeing is the reason this observatory exists in the first place. It was not built simply to take pretty pictures of nebulae, although it does that too, and the early images released to the public, glowing clouds of gas in the Trifid and Lagoon nebulae, sprawling clusters of emerging galaxies in Virgo, are stunning enough to make headlines on their own. But the real story is buried deeper than the pictures. This observatory was built to hunt for something that, by definition, cannot be seen. Dark matter, dark energy. According to the scientists who designed this mission, roughly 95% of everything that exists in the universe is made up of substances we cannot directly detect, cannot touch, and barely understand. Dark matter is the invisible scaffolding that scientists believe holds galaxies together, something so mysterious that we only know it exists because of the gravitational fingerprints it leaves behind. Dark energy is even stranger. a force that appears to be actively pushing galaxies apart from each other, accelerating the expansion of the entire universe, for reasons nobody has been able to explain. Now think about what that means. We have built the most powerful sky-scanning machine in human history, and its central mission is to chase at something we cannot see, to measure a force we cannot touch, in order to understand 95% of a universe that has been hiding in plain sight since the beginning of time. This is not chaos, this is strategy. A deliberate, decades-long bet that if you watch the sky closely enough, for long enough, the invisible will eventually leave a trace. But the deeper you go into this story, the more layers start to peel back. This observatory is named after Vera Rubin, an American astronomer whose work in the 20th century quietly rewrote our understanding of the cosmos. Rubin studied the rotation of galaxies and found something that should not have been possible. Stars on the outer edges of galaxies were moving far too fast. Under the normal laws of gravity, based on the visible mass of those galaxies, those stars should have been flung off into deep space, scattered like debris. They were not. Something invisible was holding them in place. Something with mass, with gravity, but with no light of its own. That discovery became one of the strongest pieces of evidence that dark matter is real. And decades later, an entire observatory now bears her name, built specifically to finish the investigation she started. This is where the story stops being about a telescope and starts being about something closer to an unfinished mystery, one that has been quietly unresolved for over 50 years, and is now being handed the most powerful tool ever, built to crack it open. And the timeline only adds to the tension. The observatory's real mission, officially called the Legacy Survey of Space and Time, is a 10-year commitment. Not 10 months, not 10 weeks of headlines and then silence. 10 full years of continuous nightly scanning of the same patch of sky, building what scientists describe as the largest astronomical movie ever created. An ultra-high-definition, time-lapse record of the universe changing in real time. According to project leadership, the amount of data collected in just the first year of this survey is expected to exceed everything gathered by every other optical observatory in human history, combined. Read that again. 1 year of data from a single machine will outweigh the accumulated output of every telescope ever pointed at the sky before it. This is the point where most explanations stop. They tell you the numbers, they show you the pictures, and they move on. But what most people are not seeing is what happens after the data is collected. And this is where the story takes a turn that almost nobody outside the scientific community is talking about. Because of how sensitive some of this data can be, the observatory's alert processing is not handled in some open university lab. According to information released about the system's architecture, certain types of alerts are processed at a classified United States government facility in California. The reason given is straightforward on the surface: to screen for events that might accidentally reveal the location or behavior of classified government assets, things like military or intelligence satellites that could be mistaken for natural celestial objects. When something like that is detected, it gets temporarily redacted, held back from public release for a window of about 3 days, until the information is no longer considered sensitive. Think about what that actually means. A civilian science telescope, built to study galaxies and dark matter, scans the sky so completely and so precisely that it is capable of accidentally photographing classified government hardware in orbit. And there now exists a formal government process to intercept and redact that data before the public ever sees it. This is not science fiction. This is the operational reality of a telescope currently running in Chile. And here's where everything changes in how you should think about this project. Despite that redaction process, the observatory's core philosophy is built around radical openness. Once an alert clears that brief screening window, there is no proprietary holding period at all. According to the people who designed the system, the goal is to transmit nearly everything the observatory knows about a given event to the public almost immediately, so that scientists anywhere in the world, not just at major institutions, not just at well-funded universities, can act on it in real time. This is a strange and powerful contradiction sitting at the heart of the project. On one side, a layer of secrecy serious enough to involve a classified government facility. On the other, a commitment to open data sharing more aggressive than almost anything else in modern science. The same machine that might accidentally photograph a spy satellite is also designed to instantly hand raw cosmic discoveries to amateur astronomers, students and citizen scientists around the globe, with no embargo, no exclusivity, no gatekeeping. But here's where it gets worse, in the sense that the scale of responsibility only increases the longer you sit with it. Among the objects this observatory is specifically built to detect are near-Earth asteroids, space rocks whose orbits bring them close enough to our planet to matter. In its earliest test observations alone, the system identified 7 near-Earth asteroids. Officials were quick to clarify that none of these particular objects pose any danger, but the deeper implication is harder to dismiss. If a brief test run, lasting only about 10 hours, was enough to find 7 near-Earth objects, what happens when the system runs every single night for 10 consecutive years? According to the project's own projections, Rubin Observatory is expected to discover the vast majority of large near-Earth asteroids that exist within reach of current detection methods, dramatically expanding humanity's map of objects that could, in theory, someday cross paths with Earth. This is not about prediction or panic. It is about visibility. For the first time in human history, we are building a system capable of actually seeing the population of objects sharing our orbital neighborhood, instead of guessing at it from incomplete data. What we choose to do with that visibility, how seriously governments and scientific institutions act on it, is a question this generation has never had to answer before, because we never had clear enough eyes to ask it. And the asteroid count keeps climbing far faster than even optimistic early projections. According to a press release issued in April of this year, before the full 10-year survey had even officially begun, the observatory had already gathered what officials called its largest asteroid haul yet, and described it as merely the tip of the iceberg. Earlier figures from February put the early discovery count above 11,000 new asteroids, with tens of thousands more measured and cataloged in the same window. These numbers were generated before the formal legacy survey of space and time had even started. This is the equivalent of a machine breaking records during its warm-up laps before the actual race has begun. Think about what that pace implies. If this is what the system produces while still in a commissioning and testing phase, the real 10-year survey is not just expected to add more data, it is expected to fundamentally transform our catalog of the solar system, identifying potentially millions of new asteroids within just the first 2 years of full operation. This single observatory alone is on track to outproduce the entire combined asteroid hunting effort of every other telescope on Earth. But the implications stretch far beyond rocks and orbits. This same system is designed to catch supernovae, the explosive deaths of massive stars, in the act, in real time, instead of discovering them days or weeks after the fact, which has long been the limitation of traditional astronomy. It is built to catch the flickers of variable stars, the kind of subtle pulsing brightness changes that can reveal hidden details about how stars are born, live, and die. It is built to catch active galactic nuclei flaring to life, the telltale signature of supermassive black holes feeding at the centers of distant galaxies, waking up and devouring matter in violent bursts of energy that ripple outward across unimaginable distances. And this is where the scale of the project becomes almost impossible to fully process emotionally, even as the numbers stay perfectly factual. According to project estimates, over its 10-year run, Rubin Observatory is expected to catalog millions of supernovae, image approximately 20 billion galaxies, and capture roughly 17 billion individual stars within our own Milky Way. Billion, not million. 20 billion galaxies, each one potentially home to hundreds of billions of stars of its own, mapped, measured, and recorded by a single instrument on a single mountain over the course of 1 decade. We are not talking about expanding our knowledge of the universe by some small incremental percentage. We are talking about a fundamental generational leap in how much of the cosmos human beings have actually documented in detail. Everything that came before this, every telescope, every space mission, every painstaking decade of astronomical observation throughout history, is about to be dwarfed by a single facility's first year of operation. So why isn't this front page news around the world every single night? This is, in many ways, the real story buried underneath all the numbers. According to people close to the project, part of the challenge is precisely the scale itself. The volume of data is so overwhelming, 10 terabytes of imagery captured every single night, that even the scientists running the observatory have had to build entirely new categories of automated software just to keep up with their own discoveries. Human astronomers cannot manually sift through 7 million nightly alerts. The system has to do most of the identifying, classifying, and flagging on its own, using specialized detection software built specifically for tracking objects moving across the sky. In other words, we have built a machine so powerful that no group of human scientists could fully process its output without relying on the machine's own intelligence to summarize itself for us. Think about what that says about where we actually are right now, technologically. We are no longer simply pointing instruments at the sky and writing down what we see. We are deploying autonomous, AI-assisted detection systems processed at a scale involving classified government infrastructure, generating more raw astronomical data per year than the entire prior history of optical astronomy combined. And most of the public conversation around it is still limited to a few viral images of glowing nebulae. The pictures are beautiful. They are also the smallest part of the story. The real story is the decade still ahead. The legacy survey of space and time has barely started. According to the project's own published timeline, Deeper data releases are scheduled to roll out gradually over the coming years, with the next major release expected later this year and a full first formal data release planned roughly 2 years after the surveys start. Each one of those releases is expected to reveal more than the last. Each one is expected to push the boundary of what we understand about the structure, history, and ultimate fate of the universe a little further outward. And somewhere in that decade of nightly scans, something is going to be found that nobody is currently predicting. That is not speculation for dramatic effect. It is, according to the scientists themselves, one of the most likely outcomes of running a survey this comprehensive for this long. Historically, every time astronomers have built an instrument capable of seeing more of the sky than ever before, in more detail, with more consistency, they have stumbled onto categories of objects and events nobody had anticipated, new types of stellar explosions, new classes of asteroids, entirely unexpected behaviors in galaxies once assumed to be simple and predictable. Somewhere in the next 10 years of data pouring out of Cerro-Pachon, there is very likely something waiting that does not fit cleanly into any existing scientific category. Something that will force astronomers to revise textbooks, rewrite models, or admit that an assumption held for decades was wrong all along. We do not know what it is yet. Nobody does. That is precisely the point. What we do know is this. One mountain in Chile is now home to the most powerful sky-scanning instrument human beings have ever built. It is currently capturing the universe in more detail, at a faster pace, with a wider field of view than every prior telescope in history combined. It is hunting for invisible matter and an unexplained force that together make up 95% of all existence. It is finding thousands of new asteroids before breakfast. It is photographing objects so sensitive that a government facility has to screen them before the public sees them. And it has barely been running for a year. So the question is no longer whether this observatory is going to change our understanding of the universe. The evidence already shows that it is, night after night, image after image, alert after alert. The real question, the one nobody can answer yet, is what happens when 9 more years of this kind of data finishes accumulating. What gets discovered in year 3, year 5, year 8 that nobody saw coming tonight? What invisible piece of the cosmos finally becomes visible after 50 years of searching because one telescope on one mountain simply refused to stop watching? Somewhere above Cerro-Pachon right now, the sky is being recorded in more detail than it has ever been recorded in the entire history of our species. And whatever it is hiding up there, whatever has been waiting in the dark for someone or something to finally look closely enough, that answer is still out there, somewhere in the data, waiting to be found.